In this video I'm going to discuss two types of reactions. I'm going to briefly go over dissociation reactions, and then the majority of the time I'm going to be discussing precipitation reactions, and how to identify them, how to write them out, how to interpret them. Right? So dissociation reactions, just as it sounds basically, it's when you dissolve some kind of ionic compound in water and it breaks up into its ions. So let's write out a few here. So we have solid NaCl. We dissolve it in water, and it's going to form aqueous Na+, and aqueous Cl-. So this AQ, that means aqueous. That just means that it is dissolved in water. So that's a state of matter that you'll see a lot. It just means dissolved in water. Right? And ionic compounds will always break up into their ions if they are able to dissolve in water. But as you'll see throughout this video, not all ionic compounds can dissolve in water. So if we have, let's do another dissociation reaction, CaCl2. So we put that in water. So that's going to form, so calcium is a group 2 metal. So group 2 metals always form 2+ ions. Now this 2, that means that there are 2 chlorines in that molecule. So that means that we're not going to get a Cl2- ion. Chlorine's never going to form a 2- ion. Instead, we're actually going to get 2 separate Cl- ions. So this subscript just becomes the coefficient for its ionic form. Right? So let's do one more. 2. So take a few moments, pause the video, and see if you can figure this out on your own first. Okay, hopefully you did that. So now, remember the subscript for aluminum is 2. So that means that we're going to have 2 aluminum ions. And aluminum is always going to have a 3+ charge. And this SO4, that's one of your common polyatomics. That's sulfate. And sulfate always has a 2- charge. But don't forget, outside of the parentheses, so outside of this polyatomic, you have this subscript of 3. So that means that you're going to get 3 sulfate ions. But those sulfate ions are going to stay together. Remember, polyatomic ions are not going to break up. So that is the dissociation reaction for aluminum sulfate. Right? So with that in mind, let's talk about precipitation reactions. So what is a precipitation reaction? Well, when you hear the term precipitation, you will generally think of rainfall, snowfall, something like that. And in meteorology, that's accurate. But in chemistry, the word precipitation has a different meaning. Precipitation in chemistry means when a solid forms from an aqueous solution. So what you want to look for a to identify a precipitation reaction, and you will sometimes have to identify reactions as precipitation. Basically, you want aqueous reactants coming together to form at least one solid product. So for instance, let's say we have So we have 2 aqueous ionic compounds. We have lead nitrate, lead-2 nitrate, and potassium iodide. And they come together, and they do form one aqueous compound, which is fine. That's almost always going to be the case. But they also form one solid compound. So what that means is basically we take both of these and we dissolve them in solution. So we have a solution with no solid at the beginning of the reaction. Everything's dissolved in the water. But as these mix, they start to form this one compound that is not soluble in water, so that's referred to as insoluble. INSOLUBLE. And if it's insoluble, it's going to precipitate out of solution. It's going to solidify. Okay? So solids in these reactions are insoluble compounds. Okay? So that's how you identify a precipitation reaction. Now, from there, you can actually look specifically at the precipitation process. The way you do it is by using a net ionic equation. So this form of the equation is referred to as the molecular equation, because we are showing these molecules in there as molecules. We're not showing any ions or anything. So the next step from there is to look at the complete ionic equation. So for that, any species, any ionic compounds that exist in the aqueous state of matter, you want to actually break them apart into their ions. That's why we talked about dissociation reactions here in the beginning. You're basically going to show the dissociation products for anything that you see as aqueous, right? Because, as I said here, once we actually dissolve the solid and make them aqueous, they do exist as in their ionic form. Anything that is not aqueous, just leave as is. You're not going to change anything about it. So, lead nitrate. We've got nitrate has a -1 charge. Hopefully you're aware of that. That's one of your common polyatomics. And there's two of them. So that means the charge for lead, to make it electronically neutral, has to be a +2. So we have a Pb2+ ion, and it's aqueous still. We have, remember the subscript goes before the polyatomic, so we have 2 NO3- ions, plus. This one's also aqueous, potassium iodide. So now this 2 gets distributed to both the potassium and the iodine. So potassium iodide just breaks up. A single molecule of potassium iodide will form one K+ ion and one I- ion. You know that because potassium is group 1 and iodine is a halogen. But we have 2 molecules, so you'll end up with 2 of each. So you get 2 K+ plus 2 I-. Now I'm just going to continue below it just because I ran out of room. So remember, this is solid, and if you have anything that's not aqueous, you don't change it. So just rewrite that in the exact same form as its molecular form, because it does not form ions because it doesn't dissolve. Plus, now this one is aqueous, so we can distribute the 2, and we can say 2K+ plus 2 NO3-. Okay, so that is your complete ionic equation. Now the last step is to get the net ionic. So for the net ionic equation, all you're going to do is take the complete ionic equation, and anything that exists in the exact same state of matter, the exact same state completely, on both sides of the reaction, both the reactant side and the product side, you're going to cancel them out. So for instance, we have lead 2+ here. But lead on the product side is as a solid molecule. That's not the same state, so we can't cancel those out. We have 2 aqueous nitrate ions in the reactant side, and we have 2 aqueous nitrate ions on the product side. They are the exact same state. Those cancel each other out. Okay. We have 2 aqueous potassium ions on the reactant side and 2 aqueous potassium ions in the exact same state of matter on the product side, so those can cancel out. And iodine cannot get canceled out because that's also in the molecular form of the product side. Now let's say for instance, if you had like 2 nitrate ions on the reactant side and 1 on the product side, you'd be able to cancel out 1 from each of them. So basically you can keep canceling out until you no longer have it on both sides. Okay, so now we've canceled out everything we can, so we'll just rewrite this equation with anything that is not canceled out. So we have Pb2+ aqueous plus 2I minus aqueous produces solid PbI2, and that is your net ionic equation. And that also happens to show the precipitation process. It shows you that one lead ion will come and will bond with 2 iodine ions and form this lead 2 iodide. Now, one last thing I want to mention. So there will be sometimes that you'll have to identify that you may not be told what state of matter the products are in. So you'll need to know your solubility rules. So the solubility rules, there's quite a few of them. Now, I have those posted on Blackboard to help you out. So you'll have those to look at as a guide. So you don't need to memorize them because you'll have them on Blackboard. You'll have access to them. And you'll have that for quizzes, homeworks, exams. But you do need to know how to use them. So some of the rules just outright say that everything is... So, for instance, one of the rules is that group 1 metals are soluble. So that means that any compound that has a group 1 metal, like potassium iodide for instance, that is always going to be soluble. See, both of the ones that have potassium are always soluble. Some of the rules will say something like, this is soluble unless it's paired with these specific ions. So what that means is that if you have something like that, it will be soluble in most cases, but if it's paired with one of the specific exceptions, then it becomes insoluble. And if something's insoluble, remember, that's when it is a solid. Right? If something is soluble, that means that it's aqueous. And so I'll provide more practice, and we can do more practice together through Zoom using those solubility rules. But remember, there's quite a few of them, so you will not have to memorize the solubility rules. You just need to know how to apply them.